So I'm doing a 45 KVA. And it's a dry-type transformer. And this says it's got a 600 volt, 3-phase, 3-wire primary. And it has a 120, 208 volt, 3-phase, 4-wire secondary. So what I'm going to do is I'm going to do the beginning part on this side. So I'm going to do on the primary side. Right, so here's my transformer over here. And I've got 600 volt, 3-phase, 3-wire primary. So I'm going to do everything here. Number one is asking for the maximum size primary fuse without going to the next standard size. Then it gives a rule. 26,254 sub 1. So you can read these over as we're going. Okay. And it's got standard size fuses are 15, 20, 25, 30, 35, 40, 45, 50, 60, 70, 80, 90, and 100. And then you can go to table 13 to see the rest. This is not a multiple choice test. So those are the standard size fuses. So when I go to this rule 26,254 sub 1, it talks about rated primary current. It talks about the fuse. Not more than 125%, so it goes not more than 125% times the rated primary current. Rated primary current. You're going to see that all over the place. We're going to do transformers. We're going to do welders. We're going to do capacitors. They're going to talk about rated current. You know what that is? Well, let me do that in red. The rated primary current is equal to I. The primary, which is equal to the power, or the KVA, divided by the primary voltage times 1.732. You know what? Maybe I should have just said P over E. P over E, right? And then, okay, so it's 3-phase, 1.732. So when we increase the denominator, the answer goes down. Current goes down. That's the beauty of 3-phase, is smaller wires. Smaller wires. So this rated current here, we could calculate it out. What's the transformer over here? It's a 45K, right? 45K kilo, 1,000 VA. Primary voltage, 600 times 1.732. I know what I get. I get 43.3 amps. So you see that there? If you go to your transformer card, if you go to that, if I go back to the application here, you notice right here, 600 volt for a 45 kVA. Look at that. 43.3. They're actually, this card here gives you the rated currents, but it doesn't give you the code stuff. It only gives you the rated current. So you know what this card is? It's like a dummy card. It's like I is equal to P over E. Take the power of your transformer divided by the voltage of the wherever you are on the primary. And if it's 3-phase, which this is a 3-phase card, you could flip this around and it'll be single phase. This is what you're going to get, rated current. That's all it is. It's like stuff that you know. You already know Ohm's law. You don't really need to know this stuff here. So now that I have that, now I can put it into my, so my rated primary current, 43.3 amps. Yeah. 43.3 times 1.25 is 1.25 times 43.3, 54.125 amps maximum. Remember, not more than this. So therefore, up at the top there, you know, it falls between, you know, a 60 and a 50. Be picking. So you're going to go up to 60 or you're going to go down to 50. Therefore, use a 50 amp D. I'm going to put RK5 here, okay? RK5. So a D fuse, RK5. RK5 fuses are inrush rated fuses. So now that you're doing transformers in theory, you know, you got this coil going around an AC circuit. Why doesn't the fuse trip here? Isn't it like a whole coil of wire? Why doesn't the fuse trip? It's a coil, right? So anything with a coil, you're going to have some kind of XL. You're going to have some kind of reactance measured in ohms, which is going to limit the amount of current. So at startup, it's like a real big short circuit. But when you have a sine wave where it's going up and down, it's, this field is building and collapsing, building and collapsing, building and collapsing. And it's going like really fast. But initially, when it first turns on, boom. That's why we need this fuse. We need this, you know, inductive type fuse. Okay, so now we picked our fuse sizes. So they're 50 amp fuses in here, 3 of them. We'll go to subrule 2. Subrule 2. Number 2 on the transformer handout. What is it asking for? Size. Okay, size of disconnect. Minimum size of disconnect. Right. So now I got a 50 amp fuse. What size disconnect? 50 amp fuse, 60 amp disconnect. So now, there's nowhere in the code that tells you that. So this is going to be a 60 amp switch, disconnector switch. And these are 50 amp fuses in here. And this is a 60 amp disconnect. So if I'm not going to go to 3, I'm going to jump over to 4. 4A. 4A is over here. You want to know the minimum size of copper T90 coming into this disconnect here. From the main power to the line side of the disconnect, right here. That's 4A. And then 4B is going to be over here. So I got a rule. 14100 BI. And if you read the first part there, it says, in a general area, the wires must be sized to the switch. So it's not like a motor. This you could call this a tap conductor. But it's coming into this disconnect here, 14100. Which means that, so size the wires to the disconnect. Size the wires to the disconnect. What disconnect did I use? 60 amp. Go to table 2, 75C. and pick a wire good for the disconnect size of 60. Therefore, number 6 T90s. We're going to go in. So 4A is going to be number 6 T90s coming into that based on the switch size. Okay. And now 4B says from the load side of the disconnect to the transformer. How do we size these wires? Well, I got a rule. 26 to 56, 1A. If I read this rule, it says not less than. So you really got to watch out how they're worded. Not more than, not less than 125% times the rated primary current of the transformer. We've solved for that already. I got 54.125 amps max. We go to table 2, 75C. We use a number 6 T90. I'm just going to write over here good for 65 amps. I don't know. I just get used to writing it all the time. Good for 65 amps. Okay, so now I got number 6 is coming in, number 6 is going out. I often get asked this question. You got 50 amp fuses here. How come I can't rate my wires here based on 50? I go, good question. And you know, like maybe when you come out of the 4 walls, you'll probably get away with it. You know, you'll get away with number 8s in this transformer here. But based on you know, in 26 to 54.1, you going down to a 50 amp fuse, but your rated current is this. And so when you multiply by 1 1/4, this is what you should be sizing your conductors to, even though you went down on your fuse. So that's why we got this rule 26 to 56 1A. And there's other rules that we're going to look at as we continue with transformers. Okay, so let me erase this. Any questions with this? It's pretty straightforward. Your rated primary current is P over E. The power of the transformer is a 45 kVA, and your voltage on the primary is 600 √3. You get 43.3. Multiply that by 120. Just read the rules for transformers. There's only 3 transformers, 3 of them. There's a high voltage over 750 volts. There's other than a dry type. And then there's like a dry type less than 750 volts. That's the 3 transformers that are available in the industry. Other than like all the other liquid filled ones and stuff. But once you figured out what fuse size you're going to put, what disconnect do you need? I gave you this chart, right? Good. And then what's the wire that I need to put for this switch? Rated for the disconnect. In a general location, they want you to rate the wires for the disconnect. Are there other options? Yes. Electrical is forever, guys. Like, you can do a lot of different things out there. You know, if the fuse over here feeding into this, let's say it's a non-fusible, well, those wires could be anything coming in here, you know? It's size protected by some overcurrent device ahead of this switch. And then I wanted to know the wire size, okay, based on the switch, and then the wires from the load side to the transformer, not less than 125% of the rated primary current. It's 54, and that should be min. Not less than, so minimum. Go to table 2, 75C, number 6, good for 65. Okay? Now I'm going to flip this around. And now we're going to go on the secondary side of the transformer. We're going to go from here to the panel. So this side here is a 120, 208, 3-phase, 4-wire. You know the difference between a combination panel and a load center? Yeah, so the combination has a main. For the load center, it has no main. You might only have like just 4 lugs in it. You might have like A, B, C, and a neutral. If it's 3-phase or wire. So load center, this is a lot cheaper. This, you know, you could be running it when it's 600 volt, 3-phase equipment, like not 600 volt, but 3-phase equipment, when it's like 3-phase stuff, it starts to get up in price. Like, you know, this one here, let's say this is a, I would say a 200 amp 3-phase panel runs about $500 combination. Where the load center, this one over here, a 200 amp 3-phase, run about $200, not 200 amps, $200. So $300 difference. And if you properly size that fuse on the primary, it's considered as protecting the transformer and the secondary wires in the panel. I would take full advantage of it. I like money. Why would I put a combination panel here unless there's rules that you have to follow rules? You know, sometimes you get defects and you learn. I got a defect one time because I did this. I put a disconnect in the electrical room, the transformer in the electrical room, and I ran this all the way to the bank. And I put a load center in the bank. Defect. What? No, is that electrical room accessible 24 hours to the tenant? No. Then you're going to need to put a combination panel. So pull out the panel and put in the combination, and I ended up using this somewhere else. You know, in case something were to happen, let's say like the electrical room was in the pizzeria, and the pizza place is open like late, like 10 o'clock till like, you know, in the morning, till 4 in the morning, 3 in the morning. The bank opens up at 8, and if there's an issue, they can't get to the electrical room because a fuse is blown. Well, that's why they want like a combination panel here, so the breaker would trip here before it got to the electrical room. So there's a lot of learning. Learning is like getting defects. Hopefully it doesn't cost you too much. So I'm going to finish off, where we finished off was 4C. So we're talking about over here now, 4C. What size wires would you need over here? Again, I got a rule. I would open up to it, 256, 2A. What does that say? Not less than 125% times the rated secondary current. Rated secondary current. Okay, so how do I get the rated secondary current? Rated secondary current equals I of the secondary, which equals the power of the transformer divided by the voltage in the secondary times 1.732. This is a 45 kVA divided by 208. Line values, always line values, times 1.732. I think I get 125 here, I'm guessing. I can go to my transformer card, the dummy card there. You can look at that, or you just take your calculator, P over E, and then root 3. You get 124.911. Not the Porsche 911, just 24.911 amps min. Oh, sorry, that's my rated current. What am I saying? That's my rated current. So on the transformer card, it'll show 125. Yeah, now that I saw that somebody just posted something there, I got to make it that because the 7 rounds it off. So my rated current is 124.912 amps. What do I get? 1.25 times my rated secondary current, P over E. 124.912. Get 156.14 amps. Min. That's key. Minimum, not less than. That's my minimum. I go to table 2, 75C, 2-aught, T90. If you want, you can put the good 4, 175 amps. It keeps you, this way you went to the thing and you verify. What's it good for? 175 amps. Will it carry 156? Yes. Okay, so now we're pretty much done all the stuff that was on the other side. I'm going to go to 3 now. See if you could follow this on your chart. Number 2 is only good for 115. Oh, okay, you went to aluminum. So now I'm into, we're going to do the panel board protection, right? So if you follow this on that sheet in the left pane, so 3 is asking for the minimum load center. Minimum load center. So I got a rule, 14606 sub 2. IP-EP equals IS-ES. The IP is the fuse, and the IS is the panel board. Okay, and you know what EP and ES is, right? Voltage in the primary, voltage in the secondary. So now I have to transpose this to get because I'm looking for the panel board here. Looking for the panel board, so I got to get I by itself, IS by itself, or you could even add this in. What fuse did we use? 50. What voltage is in the primary? 600. We're looking for the panel board. What's the voltage in the secondary line value? 208 volt. I got to get rid of the 208 here. Bring it to the other side of the equal sign. It's going to be 50 times 600 divided by 208 volt equals, so my minimum panel board, so 50 times 600 divided by 208, I get 144.231 amp min. So now if you go to the chart there, it'll say, oh, you got these panels. So now, do you go up to a 200, or can I go down to the 125? So my panel board protection, right? It's got to be 200. It's got to be 200, right? Minimum. So look at this again, 14606 sub 2. This is one of the better rules here. In the rule, it says that the panel board must be greater than or equal to the fuse times the ratio of the voltage on the primary and secondary. I get 144.3. They don't make that panel. I'd almost joke around and go, give me 144.231 amp panel. 12208 3-phase 4-wire, 144 amp. What? 144 amp. Don't they make one? No. What do you have? Bring me one that's higher than that. One that's a bit higher than that one. So he comes out with the 200. That's it. So this will be a 200 amp panel. Because a 125, no. So the fuse that you put will not, and it, you can do a quick check. What would be the max fuse I can put on a 125? Okay, so I go to this. What would be the max fuse? Max fuse for a 125 amp panel. Load center. Okay, so I go to this formula. IPEP, ISES. Remember, VA in equals VA out. Higher voltage, lower current. Lower voltage, higher current. VA in equals VA out. That's what you guys were working on in theory. If you could just use the VA and transpose to get the current. If you had like VA equals E times I times 1.732, and you want to find this, and maybe that's in the primary, transpose it, get these two to come down. VA over E times, that's what this is. That's exactly what we're doing here. Stuff that you did in theory, we're doing in code. Well, I have 125 amp, I'm going to erase this in a sec, times 208 equals 600, and I'm looking for the fuse here. The fuse. I got to get this 600 to the other side. So my fuse would equal 125 times 208 divided by 600. 125 divided by 208. No. 125 times 208 divided by 600. 43. Here's the question now. Let's see if you know what's going on here. Do I go up to a 45 or down to a 40? You go down. You go down to a 40. And if you're not sure, like if you said 45, put it back into the formula. Put it back into the formula right here. Go 45 times 600 times 208. Go like that. Go, okay, I'm not sure. 45 times, I love math. For math, it's perfect because I got 129 amps. Well, can I go down to a 125? No. So then there's no way you can use a 45 amp on a 125 amp panel. You're going to see this again. I'm doing all this because it's going to make your life easier next week. I'm going to erase this. Yeah, so that's what you got to watch out for. But the code says it. Not less than. The panel board must be greater than. The code, like you don't have to memorize it because it says it. Right? There's no way I'd be able to memorize it. Mins and max, mins and max. So my minimum panel would be a 200 amp. .5A. So the 5A was the one coming into like this. So this is this. This would be 5A over here. What size pipe? What wires did we run into that disconnect on the prime? Number 1690s, right? And how many were there coming in? 3 wire. So 3 wires. Number 6. And I'm using EMT. Can somebody go to table 10A for a sec? Table 10A. Look up the area in millimeters squared for number 6 T90. 32.71. Okay. Okay, so that's the area of a number 6 T90. 32.71 millimeters squared. I got 3 wires, so I'm going to go 3 times 32.71 millimeters squared equals right on 98 because it looks like there's some odd numbers like 3, 21, carry the 2, 6, 98.13, right? Something like that, right? Okay, millimeters squared. And okay, so once I know that, I go to table 8. Table 8, right? Table 8's a waste of time. Table 8 says 3 or more 40% column, right? We always use the 40% column. Every time you size a pipe, 40% column. Don't worry about the other ones that say 1 and 2. Don't worry about the percentages. I get asked all the time. 40% column. Of which table? For EMT. So EMT is table 9I. Right? 9I. And I got to go to the 40% column. And I'm going to pick something greater than 98 point, something equal to or greater than 98.13. And I'm almost thinking it's a 21 trade size. Okay, 21 trade size. Okay, so that's how you size the EMT pipe with the wires in it. Pretty straightforward. There's no bond in there because it's EMT. You don't need a bonding conductor for an EMT. We're going to talk more about that in prints as well. Okay? And then 5B is right here. Well, guess what? What did you use here? Number 6s? What did you use over here? Number 6s. So I'm just going to say same as 5A. 21 trade size. Okay? Now 5C is here. Well, what wires did I use over here? 2/0. T90s. How many were there? 4-wire, right? 4-wire, yes. There's 4 of them there. So I got to go to table 10A. What's the area of 1 2/0? I think it's 144. 144 millimeters squared. How many wires are there? 4. That equals 576 millimeters squared. I remember this one. Forget about table 8. Table 8's a waste of time. So I'm going to go to table 9I. I'm going to go to the 40% column. I'm going to find something greater than this. What is it? 53? Okay, so I got a lot of 53s. Good. 53 trade size. So now what we've done is we've sized the primary fuse, the primary and secondary conductors. We've sized the pipes, the panel, and the wire coming in. The last thing is the bonding conductors. This is very important. Bonding conductors. So I'm just going to go like this. I'm going to do like a transformer like this. I'm going to say you want me to do. I think when you look at your chart there, this is 6, this is 7, and then they want you to bond the XO of a transformer. So now, with transformers, the new rule for this code book is you don't have to ground them anymore. You've gotten rid of this rule. All you have to do is put a little bonding jumper from a lug to the XO. Crazy, crazy. You don't have to go to the copper pipe anymore. You don't have to go to an electrode. Unbelievable. I don't know. I don't know how they decided equal potentiality. And I'm like, okay. So if this was flex, and this was flex, because sometimes people use flex. We want to size the bonding conductors here. So for number 6, I got a rule 10, 6, 14, 3, 3. I don't remember if it's 3A. That's why I kind of just stopped there. Let me see. I'll go to my rule here on the thing here. 3A. Okay. No, you don't ground the transformer anymore. You didn't know that? I found out kind of like the hard way. I kept going with it, but they got rid of it now. You don't need to ground. You only have to bond from the lug. We'll see. We're going to get to this. So here, it says here that the bonding conductor is based on a fuse. Based on a fuse. I ran a run. You know what that's called when you run bare bonding in a concrete slab? Field assembled. Ever heard the word field assembled? You can run 6 meters of bare bonding conductor in a concrete slab and get a ground. But you don't need it anymore. What do you need to ground? Your main service? If it's the main service, yeah, you could do that. Field assembled. So it's based on a fuse unless the wire is being used for voltage drop. Do you notice on table 16, you got, table 16, if you go to 16, it says based on the overcurrent device and based on the largest ungrounded conductor. The only time that you size your bonding based on the conductor, it's when it's being used for voltage drop purposes. Okay, that's the only time that you use the conductor to size your bond. When it's being increased because of voltage drop. Other than that, the primary, so over here, number 6 is in the primary, right? What fuse did we use here? 50 amp. Your bond on the primary, right here, is based on this fuse here. What did we use? 50 amp. Go to table 16. Why? So when I get there, do I go up to 60 or down to 30? I go up to 60. I think it's a number 8. AWG. Go up. You got to pick a number 8 bond. So you got a number 8 bond over here if you're using flex. Number 7. Same rule. Was it a number 10? Up to 60, yes. Okay, number 10. Is up to 100 amp, then it's a number 8, then 200 amps a number 6, yes. Yeah, so it's a number 10. So I'm going to run number 10s in here. Good. Yeah, I thought right away, I'm not even looking at the book. So I got this rule 10, 6, 14, 3A. It's beautiful. If you look, you got to read this rule here. And you also got to go to, read Appendix B as well. Really got to read that, because you know what? Is there a fuse on this side? There's a load center. And the only fuse I have is on the primary. You might have to increase the pipe size. Well, first of all, EMT, do you need a bond? No, you don't need a bond, okay? You don't need a bond in EMT, but if in a piece of flex, you do. So yes, you might have to increase your pipe size because of the bond, right? I'm not going to size the pipe with that as well, So when I go to Appendix B, you know what it says? Use the voltage ratio. It says the voltage ratio times the fuse. This is one of the most popular formulas I found with transformers because you're using it to size the panel. You're using it to size the bond. You're using it to size even this one over here, this bonding jumper. So that's how you size the bond on the secondary side of a transformer where there's no overcurrent device. So over here, I got 600 volt, 120, 208. What's my voltage ratio? 600 divided by 208 times the fuse. So 50, I think it's 144. I'm going to do it again. We see 50 times 144. 144. Go to table 16. And pick a bond greater than that. Number 6. Did anybody put number 6? So I'm going to need a number 6 over here. If flex was used, and I got my 2 aughts over here, and I got a fuse of 50, this bonding conductor here is based on a fuse, but there isn't one here. There's no fuse here. If there was, you would base it on a fuse, but there isn't. They're saying, take this fuse and the voltage ratio to size this bond. And the last thing is to size number 8. Number 8, rule 10.6.14, 1. You know what they say there for bonding jumper? Ratio. Take your voltage ratio times the fuse. Same rule. Same rule. You really got to look at the Appendix B and these rules. They've really cleared it up now for transformers. I actually like it. You know, that they've added in. You got to look at the keywords. You got to take your time and read those rules. 10.6.14 for bonding. So I take my voltage ratio. It's going to work out to the same as over here. I get 144 amps. Go to table 16. And again, it's going to be a number 6. So that's what I was saying to you, that if you're using flex, the ground, I don't have a green, maybe a few. The ground that you run from here, the bonding conductor that you run from here to here, just run it straight through the lug to XO. And then same here, this bonding conductor would go from here and then bond to the lug over here. That's all. If flex was used. If it's EMT, we're saying, yeah, EMT's already got the bond. You just put a little jumper here. How do you size the bonding jumper? The fuse and the voltage ratio to size that. You no longer have to run the ground to the pipe anymore. And some electricians that do, the inspector's telling them to take it out.